So yesterday I said that we'll do some problems, right? So let's try to look at some problems. Okay, so we have a straight wing, but having dihedral only for this part. Okay. Span of the wing is B and half span is B over 2. Right. What I want to measure is CL beta which we get from this kind of arrangement. Okay. So you can assume that the dihedral angle is this, same on both sides. Can assume it to be symmetric. Okay, about this. How do you go about solving this? I want to find out CL beta. So I will assume that there is a beta, positive beta coming from this side, right? What is this side called? The right side of the wing? Starboard, right? The right wing into the wind is the starboard. And this is the port side. So positive beta is right wing going into the wind, right? So I want to find out this parameters CL beta. Okay. Let's consider this small airfoil section on the wing which is at a distance y from this center line. And let us assume that there is a rectangular wing, so C is not changing, okay, it is not a tapered wing, right. So chord length of each section on the wing is same, okay, we will assume that. right. So, if you remember, we said that this section is going to see a wind which is upward, right, isn't it. So, you have a wind component which is normal to this section, that is going to be that is going to give us an increase in angle of attack at that particular section, right, and that delta alpha y. So, this angle of attack that you will see on this section is a positive angle of attack, right, because the wind coming from this side, positive side slip. So, delta alpha at y, location y, is beta into the dihedral angle, right. Similarly, if you take the section at a distance y on the other side, that is going to see a decrease in angle of attack, right. So, this aircraft is flying level flight, lift on both the sides are balanced, so that we do not have any roll. Now, there is a roll upset, because of which there is a side slip angle introduced, right. I want to find out what this CL beta is for this particular kind of wing, right. So, this is for the starboard side. Positive angle of attack, right. Delta alpha y is minus beta into dihedral angle on the port side. Because of this delta alpha, we are going to see a corresponding change in the lift, right. So, delta L y is q into that area, right. So, c into dy, right, chord length into that strip length. CL alpha, which is of the wing, into delta alpha y, right. All right, so this is and moment is what we want to find out, right, moment because of this force. So, that moment is in the negative direction. So, z is going towards y, so that we are getting a negative roll. So, L prime is the sign we are using for the roll moment. Right, and this I will get from the two sides of the wing, and both of them will add up. So, delta or if I want to get the total value two into, right. So, plus delta L minus delta L, both of them are going to give the same negative rolling moment. So, I have to add them up. And this y is going to be starting from this point y1. So, change in delta CL, the rolling moment coefficient, that has to be now found out keeping the wing as reference condition. So, QSB into delta CL, right. There is a change in rolling moment coefficient. So, remember that we are measuring this beta from the 0 condition, right. So, you can consider this beta as also delta beta, or no change in the side slip angle. We are flying level, and from the level condition is when your side slip angle is 0, and now we are talking about a disturbed situation when the side slip angle is positive. So, we are measuring this beta from that 0 beta condition. So, we can take this also as delta beta. So, what you get here is and this S is C into B, right, the wing landform area. C into B over okay. So, This is how you will find out CL beta, right. So, any other condition also given, you should be able to determine this. So, this problem is there in Nelson, it is not the solved problem, the exercise problem. Okay. Now, let us look at some example problems. So, here is our runway and an airplane is about to take off. So, it is already aligned with this center line and suddenly there is a wind, constant wind from the side. Okay. So, the magnitude of that is 8 meter per second. So, airplane is ready to take off and it is detected that there is a wind of this magnitude coming from the side. Now, you should remember, when a aircraft is taking off, it has to take off, not that it has to wait for the wind to go away and then it will take off, right. Some of the airports like Chicago or LA, you will see that every single minute there are some 2-3 flights taking off. It is amazing scene, just sit there and see. So, you will not see the strip void of airplane, so all the time going one after another. So, that kind of traffic. So, you cannot just wait for the wind to go away and then you take off. Okay. So, because of this crosswind, now we should use the rudder to trim the aircraft so that it can go along this center line, right. So, the problem is to determine the rudder angle required to maintain a steady normal heading along the runway right, and the data given is so wing loading is given, span B, span of the wing is 25 meters, wing planform area is 70 square meter, So, to take off with no rudder, your velocity should be 1.2 times v stall, right. Left curve slope of the vertical tail sin beta fixed. Okay. No, we talked about remember we talked about stick free stability and stick fixed stabilities. In this case, this Cn beta is for rudder which is fixed. So, vertical tail volume ratio and the tail efficiency factor. And rudder effectiveness parameter, right. Can you see this, all of you? So, I want to determine the rudder angle required so that I can fly along the runway, and there is a side slip because of the crosswind. So, what is the magnitude of the side slip angle? So, for that I need to know first the velocity, right. So, how do I go about finding that? Right. So, you know CL max, you can find out what is V stall. Right. So, you can find out what is and assume it to be at sea level conditions. So, rho can be taken as one 1.225 kg per meter cube. So, if you use the data, you will find that V stall is 47.6 meter per second. So, side slip angle can be calculated using this crosswind speed and the V takeoff, right. So, V takeoff is so beta is this you can find this. So, remember I want to kill the moment created because of the side slip using rudder, right. So, this sigma n, sum of yawing moment from different places, right, different contributions, has to be 0, right. What this means? This means right. So, Cn contribution from different sources, this gives me right. Cn beta is given, beta we have found, right. Delta R is to be found. So, I should know what is Cn delta R, and Cn delta R you can find out from the information given here. For example, this rudder effectiveness, the lift curve slope of the vertical tail. So, Cn delta R is here I am not accounting for the side wash angle, okay. So, that information is not given. So, I can straightway write this expression for Cn delta R. This is exactly same problem as when your aircraft will have asymmetric throttle condition, right. Let us say you are flying your aircraft and one engine fails, then how do you trim your aircraft to follow the same path, right. So, the other example is that asymmetric power condition. So, each engine is producing thrust which is 10 kilonewton, and the engine is located at a distance 5 meter from the center line. Alright. So, one engine runs out, that means you have an unbalanced yawing moment. So, if this runs out, I will have a positive or a negative yaw moment, right. So, if this engine, let us say here the thrust becomes 0, then delta n due to 2, Cg is located somewhere here, is minus 50 kilo Newton meter, right, and this I have to kill using rudder. Rudder should be powerful enough to kill this yawing moment or balance this yawing moment, right. So, I am using the this is the equation that you have to use. So, rudder deflection should be in which direction? Should be to your right or left. So, if I am having this vertical, so rudder deflection should be which side? This side or this side? This side, right, because you have to create a left on this side or side force, right. And that deflection of rudder is what, negative or positive? All control derivatives are negative, right. So, positive rudder deflection should give you a negative yawing moment, right. So, here I am deflecting rudder to this side and it is giving me a positive yawing moment. So, this deflection on this side is negative. Let us use the same data. So, Cn delta R is minus so actually this plus this should have been equal to 0. So, I have already taken care of that. So, now I am taking it on the right hand side, I am writing this as positive. So, here the S given as I think Cn delta R is not that, but Cn delta R is minus 0.001 per degree. And the velocity at which its flying level when it runs out of the engine is 100 meter per second and it's at sea level conditions. So, you can take this rho as 1.225, right. So, this is half into delta R Okay, so now I am going to stop at this stability and control, static stability and control, okay. And then we are going to start with dynamics, right. So, it's very appropriate time. So, I will just give you a brief outline, okay, what we are going to see in the next part of the course. Static stability criteria, Cm alpha should be less than 0 for pitch static stability. Cn beta positive, or directional stability, right. Now, let us say we met all these criteria. So, should we assume that the aircraft is going to fly stable in all flying conditions? What we have looked at so far is the aircraft tendency to mitigate the disturbance, right. That is what we have looked at so far, but we cannot say if the disturbance is really decaying, right. So, you have a level flying condition and then your aircraft is disturbed, so that alpha is changed, right. An aircraft has a natural tendency because of this term to kill that alpha, right, but is that really happening, right. That we will be able to see only when we look at the evolution of that disturbed quantity in time, right. So, we have to look at the time response of that perturbed variable, right. So, dynamic stability is related to the time response. So, our system here is aircraft, okay. Response in time when disturbed from an equilibrium flying condition, and that flying condition itself has to be stable to fly with, no, isn't it? Otherwise you can't fly it. So we are looking at stability from an equilibrium flying condition, right. What we want to look at when the aircraft is disturbed in flight, right, all the variables are actually going to be disturbed. It is not only angle of attack, because no, when the wind is coming, wind is not going to come only exactly from the vertical direction, it can come from any direction, right. So it can disturb all the variables, and we want to see if those variables are, the disturbed quantities are decaying in time or not, right. Static stability does not actually ensures that, right. So static stability only tells you that the aircraft has a tendency to kill that disturbance, right. Simplest example is this, right, this pendulum, and let us say you disturbed it. So it acquired some height or the amplitude, right, and it also sees a force which is trying to pull it back because of gravity, isn't it. So it is in the gravitational field. So whenever there is a displacement, so this position is at is the position of rest. So whenever this pendulum is disturbed from this position of rest, there is a force developed on this mass m, which is, so if I take force as the positive along theta, then this force is minus mg sin theta, right. Now let us look at how this force is changing with respect to this angle theta, right. So you have to look at the derivative of this force with respect to theta. I am checking stability of an equilibrium condition. So whenever we talk about stability, we are talking about stability about an equilibrium point, right. So my one equilibrium point is theta equal to 0, that is the position of rest, right. So I want to find out what is happening to this derivative at that position of rest, right. So at theta equal to 0, this derivative is right. So restoring force is trying to kill that theta, that is what it means. Static stability. So you only want to see how the force is developing over the body when the body is displaced from its equilibrium condition. So we said about static stability by looking at this derivative. Now what can we say about the dynamic stability of this system at equilibrium condition, which is 0. So I have to write down the equation of motion, right, an equation of motion for this. So if you have this length of the wire is L, so this force is creating a moment about this point of suspension, right. So which is right. is equal to the inertia force, right. So, the equation of motion is actually this, right. Now, what do you say about stability? This force or the derivative is appearing here, in some fashion, but what about this? Now, I have to look at the evolution of this theta in time, and what is the solution for this? Analytical solution. Is it easy or difficult to find? We are interested only in looking at the motion around this equilibrium condition, right, and the motion is the perturbed motion, right. So, we can think about a linear model, right, where I can approximate this sin theta as theta. So, one what is the solution for this? This this was slightly difficult, right, but this solution of this, what is the solution? Right, A is the amplitude, omega is the frequency. So, this is the solution of 1, right, and what is it telling you? It is telling you that when you hit this ball or the bob from its position of rest, which is at theta equal to 0, this is how theta is going to be in time, which means theta is always going back and forth around this theta equal to 0 position, right. So, what can we say about stability, dynamic stability? We can say nothing, right, about the dynamic stability. Static stability, yes, because it's at least it's going through this, passing through this 0, right. So, static stability does not really indicate the dynamic stability. Is that clear? Does not imply right. If the system is dynamically stable, will it automatically imply static stability? Yes, right. So, there is a conflict. So, we have to actually start with the equations of motion, try to linearize it around equilibrium points, and then look at the response to determine the stability, and that is what we are going to start now, right. So, in the next class we will write down the aircraft equations of motion.